Assalamualaikum. Previously we have learned how to make a slab, how to design a slab. Now we will take a problem and solve that particular problem. We will actually, in your scenario, we are going to solve a SPSC problem. Now I will initially mention that which type of problem we are going to solve here. It's the problem from concrete technology subject of SPSC commission paper 2018, question number 05. No, it's question number 5. Yes, it's question number 5. Before further producing in this question, we are not given any type of data. We are just given a slab. We are only given span length L is equal to 9 feet, and we have to design one way slab, very simply supported slab, simply supported slab. Now going towards the design procedure. Now this is the whole of our question. Now initially, before proceeding towards the steps, we actually need data. So data is initially we have span length is equal to 9 feet, okay, and FC, we are assuming our FC is equal to F of Y, and also we have to assume dead load and live load as well. Dead load, live load, lambda is equal to 1, so we are not writing it. So for dead load we have 120, we are assuming 120. If in question it is not given, it's better we should assume 120 PSF, and for live load I take 100 PSF. If in question these values are not given, dead on live load I assume these values, and F of C prime 3 and 60 KSI. So this is the data I require before further proceeding towards any step. Now what is my first step? My first step is to calculate. My first step is to calculate D minimum. D minimum is equal to L by 20, and I knew my length is 9 feet. 9 into 12 is to convert that into inches, and I got minimum depth equal to 5.4 inches. 5.4 inches. So I have taken H is equal to 6 inches, the overall depth of slab, and I am taking effective depth. D dash is equal to H minus 1 inch. Why 1 inch? Now I will elaborate a bit. Minus cover, minus half of dia. To find the effective depth we have to calculate like this, and now to further we have it 6 inches minus cover. For slab we take cover is equal to 3 by 4 inches, 0.575 inches, or 3 by 4 same, and minus 1 upon 2 dia. We assume that our dia is half inch. We are assuming our dia is half inch, which means our dia is equal to number 4 bar, because number 4 means 4 by 8, 4 suit, 4 by, to convert it into inches, 4 divided by 8, 4 by 8 is equal to 1 upon 2, so we are assuming. So by calculating this, we got our effective depth is equal to 5 inches. So this is the first step, And now proceeding towards our second step, and that will be like this. So second step is to calculate the factored load WU. So before calculating factored load, I have to actually calculate dead load. Initial dead load is equal to self weight and 120 120 is dead load given plus self weight of this. Self weight should be equal to 150. Now what is 150? 150 is equal to rho C. Density of one plate is equal to 150 pound per cubic feet. Okay. Now 150 into depth, we have given the depth of 5 to 6 inches. 6 inches, 6 by 12. So I can say that I can actually say that the dead load I got from this is equal to 75 psf. Wait a second. Oh, 75 plus 120 is equal to 195. 195 psf, and the factored load is equal to 1.2 times dead load plus 1.6 times live load, and I got that factored load is equal to 394 psf. 394 psf. We also have to calculate VU. VU is equal to WU by 2. So my shear force will be equal to actually the shear strength is not like this with respect to this formula. We have to find the critical section in our slab, and according to this problem, according to the ACI code, the critical section in the slab, now we are considering our slab is this. With blue pen, I considering my slab is this. This is my slab, these are my columns, simply supported beam, so it will look bit like this, and the critical section is not in the center. Now this is our center, and according to the ACI code limitations, the critical section is not in center, it is at this point, and at this point it is, and this distance is at a distance d from the center. This distance is d. To calculate the shear, we have to multiply our factored load with this distance. I will not this one, but actually now our distance will be, to calculate the shear will be this. We need this distance. So we have the formula for shear strength is equal to WU multiplied by L by 2 minus D. How I get this D? Now I will assume that this is my whole distance from this to this. This is L, and if I divided it by 2, I will get this distance half. Okay, this distance is L by 2. If I minus this distance, if I subtract this distance from this, I will get this distance in so if I minus this distance from this, I will get this distance in red, this I will get this is equal to this distance L by 2 minus D2. To find shear at this distance has been shown in red marker. We have to calculate this shear VU. So we have this formula. I got this value of 1.16k. I got 1.61k, and I also got mu. Mu will remain same, WL square by 8, and we got the value of 3.989 k into feet. Remember one thing, we are doing all this procedure for 1 feet width. So by designing the whole thing for 1 feet, we are actually designing for almost whole. This concludes our step number 2. Now proceeding towards step number 3. We have mu, we will calculate RU. RU is equal to, now to find this, you should watch the video of Slab Design part 1 to find the formula of RU. I can show you here. This is the formula before. These are the formulas RU and rho, and now I will go to find my RU. I got my RU after calculating from that formula is equal to 155.92 psi. Rho is equal to 0.0032. I also got my rho maximum and rho minimum. I found out that my rho was actually less than rho minimum, so I took my rho minimum is equal to 0.0033. So this is my rho which I am gonna use in this design procedure. And I got my area of steel is equal to 0.198 inch square. I got throughput rho is equal to rho b d. I took d is equal to 5 inches because this is our effective depth, and we have to find area of steel using our effective depth. And I have decided my number of bars is equal to, forgetting area of steel, I have actually haven't decided my number of bars. I have decided my number of, I have chose number 4 bar actually. Dia of bar is number 4, and my spacing at, I can say that I have chosen number 4 bar at 12 inches spacing. And how I calculate this spacing? I calculate the spacing using this formula. S is equal to 12 AB divided by area of steel. The area of steel is this. I can show you area of steel is this, and area of bar is this, his diameter. Okay, now this will conclude our 3 steps. Now what will be the 4th step? I will show you here. Our 4th step is to our fourth step is to check the moment capacity. So I got my 5 mn. I got my 5 mn is equal to 51.88 kips into 51.88 kips into inches. Wait, which road this take? We'll check that how it is in the fits. 51.88 divided by 12. I got 4.32. Right, this is equal to 4.32 kips into fit, which is actually greater than my mu value. In this fifth step, I got my 5 VC. Half of 5 VC is equal to half of 5 VC is equal to 5.9 K. 5.9 K, which is actually greater than VU. And in the sixth step, I actually designed the secondary reinforcement. Secondary reinforcement is equal to AS is equal to 0.018 into B or D, and I got my bars 4, number 4 bar at 18-inch spacing. I use the same formula of spacing as I did in the main reinforcement bar. So this concludes our whole procedure for the design of slab. Okay, if you have any queries, you can